The automotive industry, on one hand, sometimes seems like nothing has fundamentally changed. 4 wheels, an engine, a seat. Everything is the same as it was 100 years ago. On the other hand, the constant search for new ideas, through the realization of which the engineering genius of mankind is manifested. Now, we see new electric cars, which could previously be seen in fantastic films. For example, this one. Straight into your glossy paws extends the steering wheel of this futuristic Chinese car. The company that works on this masterpiece of engineering, weighing about a ton, planned its market debut this year at a price of $137,000. But the auto industry lives not only by electric cars and flying hybrids. There is still a lot of interesting things in the automotive world. In this captivating issue, we will plunge into the world of technological breakthroughs in car manufacturing. From unusual innovative engines, capable of overturning the concept of power and efficiency, to advanced active suspension systems, allowing cars to maneuver with previously unseen comfort. We will also look at breakthrough aerodynamic ideas that reshape the appearance and characteristics of cars, making them distinctly technological. But first, let's look at the historical line of internal combustion engines, which have become the norm for humanity. Look at these monsters, the biggest and strongest in the world. These are undoubtedly the RTI-96C turbocharged engines made by a Finnish company. Wärtsilä. Such engines are installed on tankers and container ships, gigantic sea vessels. The diameter of each cylinder is a whopping 96/100ths of a meter, and the piston stroke is about 2.5 meters. The working volume is 1,820 liters, which ultimately gives 7,780 horsepower. The 14-cylinder version is considered a record. The total weight of this monster is 2,300 tons. The weight of the crankshaft alone is just over 300 tons. The length of the engine is 26 and 70 meters, and the height is 13 and 20 meters. The maximum power is 108,920 horsepower at 102 revolutions per minute. Despite this, the engine is very economical. 50% of the energy obtained from fuel combustion is converted into motion. If compared with car and aviation engines, they only have an efficiency of 25 to 30%. These engines, which are called low speed, only have 100 revolutions per minute. This is done so that the engine has time to fully exchange gases, also reducing the speed of the piston movement and increasing the efficiency. But even at the most efficient and economical setting, a 14-cylinder engine burns 7,500 liters of fuel oil per hour. And there's also such a monster, a crazy tractor with almost 4,000 horsepower for just over $13 million. It's exactly this amount that the constructor received during the auction trade. Thor truck, a truck assembled by Mike Hara over 7 years. In addition to these 7 years, he invested $7 million into this machine. Usually a 12-cylinder engine is installed with only turbochargers, but Thor has an additional 8 superchargers, making their total number on 2 engines 12. To accommodate the engines, the front part of Peterbilt was enlarged. The resulting power of 3,414 horsepower at 2,500 revolutions per minute goes through a 740 transmission with a locked differential on the rear axle. When designing Thor, it was necessary to rework the suspension, as the standard one from the original Peterbilt truck was not coping, and Mike Hara replaced it with a suspension from a Van Hool tourist bus. The length of Thor is a whopping 35 meters, and the weight reaches a colossal 14,500 kilograms. This truck won't even pass over some bridges. Of course, it was created not so much for transportation, but for shows and demonstrations, as well as for extreme drag strip. 4, 3, and 500-meter parachutes are called to break the monster. There are many loud statements around Thor, like, "It's the most powerful truck ever built." It's hard to say definitively, but it's certainly one of the most striking and attention-grabbing trucks out there. Of course, the biggest, most massive, and powerful, that's cool. But if you look at it from another angle, you can see mechanisms that are no less impressive. How about an engine that can fit entirely on a coin? Yes, a working diesel engine. The main genius of these mechanisms is inventor Ronald Valentine, an engineering wunderkind who studied in Germany and started making the smallest internal combustion engines in the world. Ronald's life goal is to prove to everyone that, despite the fact that his engines are very small, they actually work. All of Valentine's engines are completely hand-assembled on a computer numerical control machine. Not a single part was created. These are high-quality small diesel beasts. The smallest of them is a diesel engine 22 millimeters long, with a piston diameter of 2 millimeters, a stroke of 3 millimeters, and an engine volume of 0 hole and 6,000 cubic millimeters, has an intake and exhaust diameter of 3 millimeters, and a total weight of just 3 grams. Nevertheless, the engine spins a 32-millimeter propeller up to 12,800 revolutions per minute. Chris Valentine made the Nano B from aluminum and steel rod. The manufacturing tolerances are up to 1/10,000th of a centimeter. Isn't this pure engineering art? Very small, but really working? Various models are presented with 3 or 2 cylinders, 2 and 4 stroke, equipped with other interesting details. Look at this. German engineers have created the world's largest 3D printed rocket engine. And what's most interesting, it's fully developed with the help of software using artificial intelligence, with no manual design involved. In simple terms, the engine was designed by a neural network. The development has a significant advantage over traditional aircraft engine designs. Its efficiency is 15 to 20% higher than that of engines with a centrifugal compressor. This is a significant improvement in rocket technology, where even fractions of a percent play a big role. The goal was to design the rocket engine as a single unit to have as little weight as possible and maximum efficient cooling. And they succeeded. The combination of artificial intelligence and 3D printing is, without a doubt, the technology of the future. How many cylinders are there in internal combustion engines? Let's look at interesting, well-known, and not so much engines, in which there can be from 1 to 64 cylinders. We will go in order, stopping at the most unusual examples. So, 1 cylinder. This is, of course, motorcycles and small mini-tractors. 2 cylinders, mostly such are put on motorcycles. They are right there. 3 cylinders. Here begin the cars, for example, Citroën, with a single 2-liter turbo engine. Yes, many people put 3-cylinder engines in their cars. 4 cylinders. There's nothing to say here. Inline 4-cylinder engines are our everything. 5 cylinders were installed by Volkswagen, Audi, and, for example, the T5 engine. 6 cylinders, classic phi-shaped 6 from I. In recent years, the 6 often changes to an 8 on many models of many manufacturers. Economy. 7 cylinders, as a rule, with an odd number of cylinders, are aviation engines, which does not prevent them from being installed on motorcycles. For example, 8 cylinders. Also very common in car manufacturing is the 9-cylinder engine. Here is definitely aviation, but there are such 10 cylinders. Can boast such an engine 11 cylinders. There is such a rare engine of the company. 12 cylinders. Such were encountered on trucks before. Today, their popularity is decreasing in favor of ecological standards. 14 cylinders. That's serious already. Such engines are found, for example, on sea container ships. The Wärtsilä engine has 14 cylinders and 108,920 horsepower, 16 cylinders. Here, what is called is rarely expensive, rich. The 16-cylinder Bugatti Veyron, 8 liters, more than 1,000 horsepower. This engine is the most powerful and complex among all serial cars. It has 64 valves, 4 turbos. The automotive industry has never seen anything like it before. However, significantly earlier, another supercar, Cizetto, was released in a limited edition, and its key feature was also a 560 horsepower engine with a V16 layout. Finding this car now is harder than finding an honest official. The number of cars produced is kept secret. 18 cylinders, the same Bugatti, but even more expensive and faster. The 18 engine installed in the 1998 Bugatti did not go into production. Anyway, nobody really counted on this. 20 cylinders. Time of monsters. 20-cylinder Detroit diesel with a power of 3,650 horsepower. Engines of this series are installed on diesel generators, drilling rigs, construction equipment, and other 24-cylinder monsters. The Ellison Company created such an aviation engine X4520 with a volume of 74 liters and a power of 1,200 horsepower. For the 1930s, it was one of the largest and most powerful aviation engines. It was intended for a very large single-engine bomber biplane. But by the time of testing, there was a transition from the use of large single-engine aircraft to multi-engine ones. This left the X4520 unused. Despite technical problems that arose during testing, 28 cylinders. In 1944, in the United States of America, the aviation engine R4360 was developed. With a diameter of 1 4/10 meters, its length was almost 2 5/10 meters. It weighed 1,760 kilograms more than other fighters at the beginning of the Second World War. However, with a working volume of about 71 liters, the engine produced up to 4,020 horsepower. A monstrous engine was produced, which, due to its appearance, was nicknamed the Cuckoo's Nest, until the year 1955. This engine was installed on several well-known aircraft: the passenger Tri-77, bombers B-36 and B-50, as well as the transport C-97 30-cylinder. Tank engine. Surprisingly, small power of 445 horsepower, created by combining 5 6-cylinder engines. Considering the arrangement of sections, the multibank, as it was called, was relatively short, but a heavy engine. Its weight was 2,379 kg, including the radiator, cooling fan, and coupling. The engine had 5 carburetors and 32 cylinders. Honda also masterfully combined a pair of 16, resulting in an H-type engine with 32 cylinders. The power of the turbocharged engine is 5,900 horsepower, 56 cylinders. The most powerful diesel engine M5 104, 5,000 HP, and, finally, 64 cylinders of Snow, which was created 5,000 HP. And, finally, 64 cylinders of Snow, which was created according to the scheme 8x8. From 8-cylinder engines, the power of the gigantic engine is 7,000 horsepower. Such engines have become the pinnacle of piston engine development in aviation. And even with the advent of the jet era, they could still compete with early models of jet engines for a long time. After all, they had many drawbacks: low thrust, high mass, small resource, huge fuel consumption, and insufficient acceleration dynamics at speeds below 600 kilometers per hour. We can conclude this brief overview here. And now it's time to move on to those engine projects that deviate from the standard schemes. Probably every second inhabitant of the planet knows how a typical internal combustion engine works. However, many companies with their developments of new engine modifications constantly surprise their offspring with grandiose success. Their internal combustion engine is supposed to literally overturn the industry. But when it comes to industrial batches, engineers always turn to the good old classic piston scheme. Every time when it comes to big money, transnational corporations prefer not to take risks. That's why it seems that the most unusual internal combustion engines have long been consigned to the scrap heap of history, and no one will return to them. Or will they? Today we will show such, and even such engines. And everything that you will see by the end of the episode will fill in for you the white spots in the history of alternative engines, and will reveal how curiously and interestingly the design thought is developing. So let's go. First in our review is an engine from an American company, which has classic intake, compression, power, and exhaust strokes. But they don't occur in the same cylinder, but in different ones. The so-called cold cylinder is responsible for intake and compression, while the second, hot one, is for power and exhaust. While the gases are expanding in the working cylinder, the cold one is in the intake stroke. In the working one, it's exhaust. In the cold one, compression. At the end of the compression stroke, the pistons approach their top dead center. The mixture is transferred from the cold cylinder to the hot one through the bypass channel and ignites. Such a split cycle is essentially the same Otto cycle, albeit modified. The Americans came up with it in 2006, and in 2009 they built an experimental Scuderi split engine cycle. The compressor and working cylinders can have different diameters and piston strokes, which allows for flexible parameter adjustment. This results in an analog of the Miller cycle with additional gas expansion. If you add a response with valves and a high-pressure balloon to the channel between the cylinders, you can make such an engine collect energy when braking and use it when accelerating. However, for a number of years now, the company's activity has been limited only to experimental samples and participation in exhibitions. It seems that the real economy here still cannot overcome the high complexity of the construction. The developers of the Croatian company also turned to the split working cycle. Their differentiated construction attracted with fewer parts, low friction, and reduced noise. The absence of oil in the crankcase necessitated an external tank for the lubrication system, but this did not deter them. The inventors built several experimental models. For a 7-liter working volume, their size and weight were nearly half that of typical internal combustion engines. But they never figured out the performance. The last prototype was assembled in 2011, and then the project stalled. The two-stroke engine, invented in 2006 in the United States of America by Walter Schmid, is even more complex. As in the project, the cylinders here are arranged in an antenna shape, and the crankshaft also performs planetary motion due to the 6-gear system. The gas distribution in the Bonner is handled by flaps in the cylinder bottoms and rotating rotors in the engine body. In this case, the outer pistons can slightly shift under the pressure of oil, providing a variable compression ratio. It's a complicated scheme, all for the sake of high power per unit of weight. Bonner seems intriguing in theory, but there's been a lack of recent news about him. Judging by everything, he did not justify the hope. Other inventors did not change the working cycles of the DVS, but focused on the position of its parts. Axial engines, patented over a century ago, are an example of such engines, as shown in the drawing above. They all differ in details, but are united by a common principle. The cylinders are arranged like cartridges in a revolver drum with a coaxial output shaft. Various systems, such as inclined shafts, oblique discs, etc., are responsible for converting reciprocating piston movements into shaft rotation. A New Zealand project of a 5-cylinder 4-stroke engine with a working volume of 3 liters is a variety of axle units. Compared to a classic engine of the same displacement, this one was, according to the author's calculations, 19% lighter and 36% more compact. It was considered for use in various fields, but dreams of conquering the whole world remained dreams. An even more complex example is the axial engine of a Canadian company. Here, instead of cylinders in a common drum, a multitude of sections are organized with the help of thin straps. In the grooves of the rotor, plates are installed that move along them as it rotates, with torque. The obtained variable volumes limit the curved surfaces. They set the trajectory of the blade movement and drive the gas exchanger. The scheme allows to create engines for different types of fuel, although initially the inventors chose diesel. In 2003, a sample was built with a diameter and length of only 152 mm. It developed 42 times more power than a similar-sized internal combustion engine. Later, the company reported the creation of larger prototypes with 127 and 380 forces. But, judging by the releases, all its activity is still within the framework of experiments. Another example of theory prevailing over practice is the Toroidal engine, or the already defunct Canadian company. The first prototypes. Engineers were testing engines with variable geometry torus as early as the year 2005. The torus acts as a cylinder, housing a rotor with 2 attached pistons that rotate within it. The variable volumes necessary for ensuring working cycles are formed between the pistons with the help of a thin distribution disc with a cutout for the piston, which is rotated by a belt or other drive across the torus. This disc limits the fuel-air mixture during the compression and working stroke. The authors of the rotary engine have eliminated reciprocating movements, hence a radical reduction in vibrations. A plus can be called a minimal number of parts and good calculated economy. In 2009, their toroidal engine, essentially repeating the Canadian one, was developed by Americans Harry Kelly and Rai Kavas. According to their assessment, a torus of half a meter in diameter would provide 30 horsepower at only 1,050 revolutions. No. There is a banner on their company's website right now saying, "Thank you for your interest. The page may be updated in the future." Perhaps a slightly better fate awaits the so-called Nutation engine, invented by American Leonard Meyer in 2006. At least a few examples of it were built. Nutation in Latin means to nod. Meyer formed 4 variable volume working chambers between the engine body and a disc that nods to the sides, which plays the role of a piston. The disc is cut in half along its diameter, and at the bottom is a Z-shaped shaft from which power is taken. The body's channels and flaps handle gas exchange. Meyer engine prototypes were built by the company and related to it. A single 4 inches disc develops 7 forces, while a pair of 0.9 inches discs develops 120 forces, 2 5/10 whole, 3 horsepower per kilogram versus 1.2 for mass-produced non-massive atmospheric engines. Some Ferrari engines produce more than 3 horsepower per kilogram, but at high 9,000 revolutions per minute, the liter power, however, is not impressive. Becker and Kinetic appear to be pushing projects to extreme levels, despite the lack of significant activity on their websites. In 2010 year, the Nutation engine fell into the zone of interest of the Research Center of the United States Air Force. Harry Smith, the lab manager, demonstrates the internals of the engine and explains what special value the design represents for light aviation. The idea of rotor aggregates of different types so often attracts innovators, as if a single deviation from the familiar scheme gives a substantial increase in characteristics. So, Nikolai Shkolnik, a native of the Union of Soviet Socialist Republics, who long ago moved to the United States of America, along with his son Alexander, developed an engine that resembles a Wankel engine, turned inside out. The rotor of peanut shape also rotates in a triangular chamber. But, unlike the Wankel unit, the seals are not on the rotor, but on the chamber walls. To develop the design, the Shkolniks founded a company that interested the Defense Agency. Now it is financing experiments in anticipation of the prospects of peanut units in light aircraft, including drones and in portable generators. The experienced engine, with a working volume of 23 cubic centimeters, has a not bad efficiency for such dimensions of 20%. Now the authors are aimed at a diesel prototype weighing about 13 kilograms and a power of 40 horsepower for installation on a hybrid car. Its efficiency, according to their calculations, should already grow up to 45%. And this is a revolutionary internal combustion engine from the company. They named it. Company representatives assert that they already have a working prototype of the engine and that they will provide more detailed information in the near future. Meanwhile, the company announced that, like the Wankel rotary engine, it does not have an offset crankshaft piston mechanism, shafts or pistons performing reciprocating motion. However, unlike Wankel engines, the Omega-1 has a pre-chamber that separates the cold intake air from the exhaust gases, eliminating the problem of valve overlap. All this makes Omega-1 the world's first engine with active linear power transmission. That is, when rotating, all power is transmitted through a single rotating power transmission shaft. The standard engine weighs only 16 kg and develops a power of 160 HP, with a rotating moment of 30 Newton. At the same time, the design easily allows for the installation of several engines one after the other, gradually increasing power. This strange development of the company has been going on for several years, during which a number of prototypes have been created, driving motorcycles and airplanes. The development represents an engine with oscillating straight-line cylinders. One end of them is fixed on a stationary axis, the other is connected to the shuttle. The authors address the so-called oscillating cylinder, primarily to aviation. Despite high output characteristics in relation to weight and dimensions, such a two-stroke unit is well suited for supercharging due to the passage of a liquid cooling channel through the stationary axis of the cylinder. With such a scheme, this trick is difficult. Well, this is a Wankel Rotary-Piston engine. Engineers Walter Freud and Felix Wankel presented this design not so long ago, in 1957. The peculiarity of such a power unit is a three-lobe rotor driven by the pressure of gases. In one full rotation of the shaft, the rotor manages to turn 120 degrees. And in each of the three isolated poles, a full four-stroke cycle of an internal combustion engine is reproduced: intake, compression, power stroke, and exhaust. The obvious advantages of this type of engine are considered to be their compactness, lightness, fewer parts, among which there are no pistons, crankshafts and crankshaft, simplified lubrication system, low vibration level, and high liter capacity. But there are also major drawbacks: poor efficiency of seals, friction between the rotor and the cylinder walls, high consumption of special oil, tendency to overheat, demand for spark plugs, and high power at relatively high speeds. The real popularity to the rotor piston engines was brought, of course, by the Japanese company, which became famous not only for its legendary models, but also for the only victory in Le Mans of the prototype 757. At different times, various manufacturers experimented with Wankel engines. Even Automotive in the 80s distinguished itself with rotary 5s and 7s, which were used in the traffic police or by power engineers. Even such a small deviation beyond the limits of traditional internal combustion engines showed how many ideas do not find mass implementation. The reason may not be a manufacturer conspiracy, but rather the continuous advancement of traditional internal combustion engines. The latest gasoline samples with the Miller cycle have a thermal efficiency of up to 40%, even without turbocharging. That's a lot. Most gasoline units have 20 to 30%. Diesels have 30 to 40%, on large ships up to 50%. And at this point, it is believed that a global alternative to the internal combustion engine has already been found. These are electric motors and power units on fuel cells, or electric cars. This is a dead-end path, and they also burn fuel, but just earlier in power stations, generating electric current. Well, since we're talking about electric cars, is there anything new in their narrow throat? In those same lithium-ion batteries, which have become the standard for the industry? Now, car manufacturers are successfully combating the drop in initial capacity through heating and cooling systems for batteries. Plus, battery chemistry is also constantly improving. But, for example, according to statistics, in the words of modern car owners, after 5 years of use and 150,000 kilometers of mileage, you still lose 5 to 10% of the initial battery capacity. But there is another type of batteries that are now used only for stationary energy storage. These are flow batteries, which are also called liquid. Flow batteries themselves consist of two tanks, with a liquid in which chemical elements are dissolved. And this is called electrolyte liquid. Each tank has its own charge, and this electrolyte liquid passes through a separator where ion exchange occurs, but the liquids do not mix. That is, as we see, the principle of operation here is the same as in lithium-ion batteries, except that the chemistry is different. For example, this is how flow batteries based on vanadium work in the company. During charging, electrolytes pass through a separator in the center of the battery, where ion exchange occurs. In the process of the redox reaction, vanadium on one side is oxidized. That is, it gives up electrons, while at the same time on the other side it is reduced. That is, it gains electrons. Vanadium flow batteries have a number of advantages over conventional lithium-ion batteries. Firstly, both electrolytes are created based on vanadium, so there is no risk of cross-contamination as the same components are used. Secondly, the capacity can be easily increased by simply increasing the volume of the tank. Thirdly, there is data on the service life, and these batteries can serve for decades without losing their properties. They can be fully charged and fully discharged without the risk of degradation. and they are not particularly critical to temperatures. Fourthly, there is no risk of ignition. And fifthly, the charge can be easily replenished. For this, you can simply replace the liquid with an already charged one. Or you can just charge from an outlet, like with lithium-ion batteries. But of course, if everything were perfect, such batteries would already be used in electric cars, not just as stationary energy storage sources. The main downside is the low energy density, which is about 5 to 10 times lower than that of lithium-ion. And therefore, such flow batteries are mainly used only in stationary sources. But a startup from 2019 is developing its own flow battery with the aim of combining the best qualities of these two different types of batteries. And now they have achieved some success. The startup, created by graduates of the Illinois Institute of Technology, Elena Timofeeva and Carlos Segre, initially conducted a series of experiments with the dissolution of liquids, various solid elements, and their ability to store energy. As a result, a multi-component material with high density was developed. It consists of nanoparticles of metal oxides, which dissolve in liquids and do not precipitate out over a long period of inactivity, after which the United States government and Army signed contracts worth more than $12 million, which helped bring the product from prototype to working model, and now the company is ready to scale up and enter the commercial field. The energy density in this liquid is 23% higher than in lithium-ion batteries. At the same time, the cost of production is twice as low, as expensive rare earth elements are not used. Losses at full charge and discharge are only 2%, and unlike lithium-ion batteries, which ignite when in contact with air or water, a liquid battery can extinguish fire. The liquid itself is similar in viscosity to motor oil. 80% of the weight is made up of nanoparticles. They claim that such a battery can operate stably at temperatures from -40 to 80 degrees Celsius. A second generation is also being developed now, where the density will be from 550 to 750 watts per liter. This will allow, for example, a Tesla electric car to travel not up to 650 kilometers on one charge, but up to 2,000 kilometers. And with this, you can replenish the full range in just a few minutes, simply by draining the discharged fluid and refilling it with the charged one. Or charge it the old-fashioned way from the grid. Moreover, the second generation will already allow using such a battery in airplanes, as the density approaches 1,000 Wh per liter. And it claims that the cost of the second-generation flow battery will still be 30% lower than that of lithium-ion batteries. In general, we just have to wait a little longer. And very soon, judging by these news, we will be pouring a new liquid into the gas tank of our car instead of gasoline, in the tank of battery cells. Well, such a liquid battery future has not yet arrived. Let's look at those amazing developments that are being implemented now, albeit not in serial models, but in premium sports examples. It caused a real furor in the world of electric hypercars. This was largely facilitated by a new power unit that replaces 3 electric motors at once. This single engine is a new unit called It produces 850 horsepower and 1,250 Newton-meters of torque. So, this electric motor has the size and weight of a conventional car's transmission and a phenomenal power-to-weight ratio. For example, one electric motor with an inverter weighs 90 kilograms and has 320 horsepower. Here, together with the inverter, that is, the system in assembly, will weigh about 50 kilograms and have a power of 875 horsepower. That is, the system is almost twice as light, and at the same time it is more than twice as powerful. And they were able to achieve this by combining the axial and radial magnetic flow in one engine. And that's why the authors call this engine raxial, from the words radial and axial, implying that the magnetic flows are directed both parallel and perpendicular. Let's move on to another engineering solution. In front of you is the linear motor generator Aquarius, with a 2-sided piston and 1 cylinder. And the price is only $100. And the weight is 10 kilograms, with a power of more than 40 horsepower. How is this possible? Here is its principle of operation. In Aquarius engines, there are just over 20 parts, and there is only one moving part. This is a half shaft, in the middle of which is a two-sided piston, which divides the cylinder into right and left combustion chambers. Also among the main parts are the engine block, two bearings, through which the hollow shaft passes, and there are also two heads, in which the spark plugs and valves are located. In this case, there are holes in the half shaft that serve for the admission of air into the cylinder, and in the middle of the cylinder wall there is an exhaust hole, which serves for the exhaust gases to exit. In the chamber, air is filled, then compressed. The injector adds fuel, and at the dead center, the spark plug sparks, and combustion occurs. Expansion of the working stroke. In this case, the rod is connected to two linear electric motors. They are located on the side and generate energy. But when the piston passes the middle of the cylinder, the exhaust port in the wall opens, and the exhaust port in the rod half also opens. The exhaust gases come out, and the chamber is filled with air again. Then the piston completes its movement to the left dead point, and now in the left combustion chamber, the fuel-air mixture is compressed according to the same principle, and all this time in the right combustion chamber there is a long enough blowdown that allows to completely get rid of the exhaust gases. And during this, the engine even cools down due to the incoming air. And the cycle repeats, that is, one piston for one movement to the right or left, performs the work of a conventional four-cylinder, four-stroke engine. It turns out that for one movement, at least 4 times more work is performed. Since here every movement is a working stroke, and there are no valves here, accordingly, there is no distribution. Also here, there is no need to convert linear motion into rotation, and therefore there is no crankshaft here. And there is only one moving element, thanks to which it is possible to achieve a coefficient of performance above 43%. In addition, due to the fact that there is no shuttle, there is no angular load and losses on friction. Since the working stroke is performed on each movement, the rotations can be kept fixed and significantly lower. Therefore, this engine is enough ordinary air cooling, which also simplifies and cheapens the design. As a result, such a motor generator weighs only 10 kg. Indeed, this is the weight of a brushless motor generator, of which there are 2 here, by the way. But this is still a very small weight. At the same time, it is capable of delivering 32 kilowatts of power, and according to the developers, the cost of this motor in mass production should be around $100. And this is not just another startup that only shows pictures. Otherwise, they would not have received, in addition to other investments, a contract with the United States Army, which after several years of cooperation was extended until the middle of 2027. After all, it's very important for the Army to have a compact and lightweight generator that can run on all types of fuel, which can be easily deployed anywhere. There's another similar scheme. Structurally, the engine is represented by 2 oppositely located cylinders, in which there are 2 pistons connected to each other, and a linear motor generator is located between these pistons. This motor generator, in turn, performs 2 functions. First, it is used as a starter, and then for generating energy from fuel combustion and piston movement. And, as claimed, the efficiency of this engine is proven and ranges from 40 to 50%. All thanks to the removal of unnecessary elements, which in this case are simply not needed. This engine completely lacks a crankshaft piston mechanism, and the motion is immediately transferred to the linear motor of the generator. Also in this engine, the side thrust is reduced. As, for example, in a conventional piston engine, the thrust is greater because the piston is directed at an angle. Also in this engine, there are no bearing shells, which allows it to operate at a higher compression ratio. And the piston speed from the top dead center is higher, which reduces heat losses. As a result, this engine is much more efficient, cheaper to manufacture, compact, and easy to maintain. And the principles of operation here are the same as in conventional engines. The presented prototype has 4 pistons with a total volume of 800 cubic centimeters and a power of 24 kilowatts. And essentially, it represents 2 engines with free pistons, where the movement occurs opposite to each other to compensate for vibrations. Auto giants, of course, are also not left out of new developments. It is also developing its own internal combustion engine with a free piston. The task here is the same as with the previous engine, to create a compact generator for a hybrid. And this is just the first prototype that we were told about and have already managed to test. This is a single-cylinder two-stroke engine with a linear generator and a unique V-shaped piston. Let's first take a look at its structure. On the left, we have the combustion chamber, the cylinder walls. We can see where the spark plug is located, and a permanent magnet is located on the piston. And when the piston is in motion, these elements will generate electrical energy. The V-shaped piston construction is shown in brown on the diagram, which is exactly what is needed for all these elements to be compactly located and functioning. And here in the back part of the piston, there are two gas spring chambers. It looks quite strange and doesn't seem very effective, but the engine was tested, and it worked stably for several hours without any problems, with a sufficiently high efficiency of 42%, and it produced 10 kilowatts of power. And it is planned to use two such combined engines in hybrid cars, which is quite enough for the car to maintain a stable speed of 120 km per hour. Also, a version without a gas spring is being designed. But initially, it is this variant that is being tested. And until they thoroughly test the new technology, it's unlikely it will be widely shown to the public. This is a promising internal combustion engine from a company that could significantly change our world. This is the most powerful atmospheric internal combustion engine to date, which meets the Euro 7 environmental standards. In the IREX engine, 2013, the best solutions from two-stroke and four-stroke engines are used, as well as from heat engines and military equipment, for example, like the engine of the T-74 tank with two pistons per cylinder. Let's figure out how it works. The cylinder block is made of aviation aluminum and has a round shape. Inside are compactly located 4 cylinders. On each side of the engine, a plate will be installed, which has bends of a certain shape, and these plates act here as an analog of the crankshaft. Next, the pistons are inserted into the groove, and then this entire construction is inserted into the engine block. On the reverse side, it's the same thing, and the plates are connected to each other. That's why this engine has 4 cylinders and 8 pistons, and essentially, these are the basic parts of the engine. As a result, it's quite simple, compact, and lightweight. And here's how it works from the inside. The entire cycle takes place in 2 piston movements. In the middle of each cylinder, there is 1 spark plug and 1 valve. And pay attention to the shape of the grooves in the piston, which is conditioned by such a location of the spark plug and valve. Intake and exhaust occur in these places. They are located at the far end points. When the piston begins to reach the dead far point, the exhaust first opens. The exhaust gases begin to exit. Then from the other side, the intake opens, the blow is carried out, and all the exhaust gases exit. Then the exhaust closes, and the intake remains slightly open, and the cylinder fills with air. Now the intake closes, compression begins, ignition, and the cycle repeats. The asynchronous opening and closing of the intake and exhaust ports occurs due to the fact that the valves themselves move slightly asynchronously. Thereby the intake and exhaust open and close in turn. To increase efficiency in this engine, another interesting technology is used. Thanks to a special rod between the valves, it is possible to change the degree of engine compression in real time. This is done, again, by slightly rotating one valve relative to the other. Thus, by slightly turning the valve, it can easily be adjusted for different types of fuel and different octane numbers, or for maximum efficiency. That is, at low load, the compression ratio can be maximum, and thus we get maximum efficiency and power at low revs. And at high load, to avoid undesirable detonation, the engine can deliver maximum power. The compression ratio decreases, and also due to this, the size of the opening and closing of the intake channel is regulated. This engineering solution is as simple as it is brilliant. Another advantage of this engine is the complete absence of vibrations. Since the pistons are directed towards each other, they move in opposite directions, and all oscillations are compensated. As for the lubrication system, it is implemented through channels, as in a 4-stroke engine. And now let's see why the Spaniards call this engine a 2-stroke. The thing is that this engine, for one full rotation of the piston, that is, for one rotation of the crankshaft, performs 4 times more work than a 4-stroke engine and twice as much as a 2-stroke one. Although, in essence, this engine operates exactly on a 2-stroke cycle, and it's more of a marketing move by the company to attract more attention. And now let's compare this engine with a 4- and 2-stroke engine, as well as with a similar engine used in heavy military equipment, and look at the pros and cons. As we know, the advantage of a regular 2-stroke engine compared to a 4-stroke is that it's smaller, lighter, and simpler, and also operates at the same revolutions. Because of this, a 2-stroke engine can deliver up to twice the power. But its drawback is the lubrication system, where oil needs to be added directly to the fuel, which is bad for the environment. In addition, part of the fuel does not burn, which is also bad for fuel consumption, and consequently, the engine's efficiency is lower. This engine has eliminated all these lubrication problems. Here, like a 4-stroke engine, there is a delay at dead points, which allows for more efficient combustion of the fuel-air mixture. The intake and exhaust are at dead points when the pistons are maximally distant from each other. The problem with a 4-stroke engine is that it's large and heavy, while at the same time it provides less power, and the design is much more complex and expensive. Compared to a regular 2-stroke engine, it has higher efficiency, reliability, and better environmental indicators. That's exactly why we all use 4-stroke engines in our cars. In turn, in engines, it was possible to significantly reduce the size and weight, and the design became simpler. There are no belts or chains here to rotate, for example, the camshaft. There are no valves here either. Plus, there is real-time compression ratio adjustment, which is implemented quite simply. And, as they claim, this engine will comply with Euro 7 environmental standards, and can also be adjusted to different types of fuel, including hydrogen. And if you compare it with a similar engine from heavy machinery, it has lower fuel consumption and lower temperature. But it has 2 crankshafts, which are connected to each other, which complicates and enlarges the construction. Here, however, it was possible to get rid of the crankshaft altogether, and there is less heat loss. The company now has 2 versions of such engines. The first is IREX, with half a liter of power and 20 horsepower, weighing only 35 kilograms. The second engine is Rexby, which can already be purchased, and the production area for its mass production is now being expanded. The Rexby engine is primarily intended for aircraft. It weighs just 1.23 pounds with a volume of 125 cubic centimeters, and the power at such a volume is 22 whole and 7/10 horsepower on gasoline. Despite this, its dimensions are such that it fits on a person's palm. Plus, the company is developing another version with a volume of 0.7 liters and a power of about 170 horsepower. And this is a gas turbine engine. Unlike many examples we've looked at, cars with gas turbine engines did exist, starting from the 50s. Light car manufacturers decided to play this game and continued right up until the end of the 60s. The gas turbine era was short, but it gave a whole range of extraordinary models: Rover Jet 1, Fiat Turbina, Ford Thunderbird, Chrysler Turbo Flight. The gas turbine is simpler and much more powerful compared to the classic internal combustion engine. It's no surprise that the automotive industry, which had actively adopted a range of technical solutions from the aviation industry even before the 50s of the last century, did not stand aside and decided to try using such engines on light vehicles. Moreover, the gas turbine engine design is not complex. Shafts with compressor turbine wheels, the first of which supplies compressed air to the combustion chamber with fuel. When combusted and expanded, the working mixture spins the turbine wheel, which uses energy to rotate the compressor and, of course, to move with the help of a jet stream. And here's a modern solution. When a small gas turbine engine is built into an electric car, The automaker is preparing to release its electric car, which it modestly named Hypercar. From a technical standpoint, everything looks quite standard for cars of this level. 4 electric motors, 1 for each wheel, where the total power is 1,200 horsepower and 1,800 newton-meters of torque. And because a small battery with a capacity of 62 kWh is installed here, the weight is only 500 kilograms, which is quite small for an electric car. But since the battery has a small capacity, another problem arises. This is a low range on a single charge, which is only 240 kilometers. And considering that the car is very powerful, the range in combat mode will be even lower. Therefore, a new development was introduced here, a very compact and lightweight gas turbine engine, which produces 35 kilowatts of continuous power. It only works at certain speeds, as a generator, and is not connected to the wheels. And since it only works in one constant mode, the developers managed to reduce the combustion temperature to 1,050 degrees, which helps to reduce the production of nitrogen oxide, and accordingly, the installation of a simpler catalyst. But indeed, this catalyst has a heating system, which is necessary to meet environmental standards during the cold start of this engine. A similar catalyst heating system can be found in a hypercar from One. Here, they managed to adapt a gas turbine engine for regular electric cars, which significantly increases the range. Now let's take a look at how this works. The gas turbine engine is capable of operating on both liquid and gaseous fuel and uses the Brayton cycle, where it spins a turbine that is directly connected to the generator. First, air is sucked in through the air intake, then it is compressed and heated. Then the compressed air passes through a heat exchanger and is further heated by the exhaust gases. Then fuel is introduced into this heated air, and the temperature reaches 1,050 degrees. And all this goes through a catalyst. Then the expanding gases start to spin the turbine up to 100,000 revolutions per minute, thereby spinning the compressor. The generator, which is located on the same shaft, also spins, and energy is produced. The cycle is continuous, and the air is constantly compressed and expanded, and the exhaust gases re-enter the heat exchanger and heat the incoming air. At the output, we get exhaust gases with a maximum temperature of 350 degrees. And thanks to this heat exchanger, only 50% of the fuel is used to increase the temperature of the incoming air. The temperature rises from 650 to 1,500 degrees Celsius. As a result, efficiency increases, fuel consumption decreases, and we get a compact generator that produces 35 kilowatts of power. It can be used in various fields. Imagine an electric car that has a very compact and lightweight internal combustion engine in the form of a generator. This is the right solution that will suit any conditions and significantly lighten electric cars, making them cheaper. But now let's look at another area of auto innovation. There are projects in the history of car manufacturing that impress with their aerodynamic solutions. For example, Gordon Murray's solution in Formula One, when he installed a fan in the rear of the car that accelerated and sucked air from under the car, thereby giving a colossal advantage in downforce, after which the race was easily won. Almost immediately, they abandoned this system as petitions were being prepared to ban this technology, and in addition, this system had drawbacks. The speed of the fan depended on the revolutions, and a lot of debris flew out from under the car. The next time Gordon implemented this system when creating his own road hypercar. And just recently, a new project by Gordon Murray appeared with a gigantic diffuser and a fan. This is the GMAT 50, and here is the fan. It is now powered by an electric motor with multiple active aerodynamics modes. Overall, it's an incredible project that is very impressive, as the car generates hundreds of kilograms of downforce at low speeds without any aggressive body kits. But a completely new, insane project has recently emerged, which has already proven in practice that it is even faster than Formula One cars. It also uses Gordon Murray's ideas, but they were brought to maximum results. This gives this electric car phenomenal turning speed, and it can even accelerate to 100 kilometers per hour in less than 1.5 seconds. And that's just on rear-wheel drive. The McMurtry's spiraling electric car with a power of more than 1,000 horsepower and a weight of less than 1 ton. The downforce is twice the weight of the car, already at 0 kilometers per hour. That is, theoretically, the car is capable of staying upside down when it is stationary, or, for example, driving on the ceiling at a speed of 5 kilometers per hour. The car has a lot of air intakes. They literally sieve this car. Their main task is to supply air to the brakes and batteries. But the air intakes are not the main thing. 2 turbines with a power of 82 horsepower were installed in the rear, which pull air from the underbody and spin the blades up to 23,000 revolutions per minute. And to prevent garbage from flying out from under the car, filters are installed here, which need to be cleaned every 3 days. And this system is capable of generating 2 tons of downforce at a standstill, which is more than twice the weight of the car. The active suspension, in turn, helps maintain the necessary clearance depending on the downforce and road conditions. And this is such an incredible value from the point of view of downforce, which is unavailable to any other car in the world. For example, track. It also generates 2 tons of downforce only when the speed becomes more than 40 km per hour. And at low speeds, this value is much less. And this also applies to a Formula 1 car and any other racing cars in general. No other car in the world can demonstrate such downforce at low speeds. So it's no surprise that after the development of the hypercar was completed, the brand immediately went to compete in the Goodwood Festival of Speed. It ends with a climb up the hill. During the storm, it flew almost 2 kilometers in just 39 seconds, breaking the previous record set by a Formula 1 car. It's funny that all these technologies were tested in a van, as there was a lot of space and it was convenient to adjust and place everything. And those who saw it from the side thought that a jet engine was installed in this ambulance, as this system makes a noise of 120 decibels. So if you don't like that electric cars are too quiet, this hypercar might suit you. Especially since you can buy it from the British for some 820,000 pounds or a ridiculous 100 million rubles. However, the car does not have access to regular roads, but it fits under the Series 1 regulations, meaning it can race on equal terms with track McLarens, Porsches, Ferraris, and others. Lamborghini. Now let's get closer to the wheels. Look at this. The Chinese electric car itself is scared of the snow. All it takes is just one button press. This became possible thanks to the active hydraulic suspension. The wheels can rise and fall within a range of 10 centimeters while driving. According to the engineers, riding in such a car turns into a flight. Indeed, what to do with roads where irregularities start from 11 centimeters is a big question. If we speak seriously, such innovations with suspension are at least a few decades away. Since the 80s of the last century, the use of an electromagnetic field has been incorporated into the Advanced Automotive Suspensions project. The idea was to create a device that would transform a rigid element into one that would dampen oscillations using the force of an electromagnetic field. Imagine a car ride that goes perfectly smoothly, without jolting on bumps and even flying over small obstacles, and also gaining energy from driving on uneven surfaces. It was exactly such a dream that the experimenters of those years were dreaming of, and this dream was realized in specific prototypes. One of the first developers of such a suspension was Dr. Amar Bose, a major specialist and innovator who also worked on innovations in the field of audio systems. The basis of his invention was a linear motor, which combined rigid elements, shock absorbers, cross stabilizers, and other familiar suspension details. A significant advantage of the developed system was that the driver could switch the required energy from electrical to mechanical. The force required for the suspension to work is generated during the ride using inactive electromagnets, which allowed for significant fuel savings. Such a suspension worked without failures, receiving energy at any time. When the entire system was secured, the electromagnetic suspension switched to a standard mode of operation, similar to many lever-type suspensions. Voltage was applied to each of the 4 powerful linear motors under the control of a central processor, and a repulsive force arose on its shaft. On 4 shafts, it was capable of lifting up to 1.5 tons, which corresponds to the average weight of a golf-class car. At the same time, the necessary chassis height was maintained with the help of a linear motor, regardless of the load. This is what is called static compensation. In addition to this, the electromagnetic suspension also created dynamic compensation, as it eliminated the car's roll. Even so-called longitudinal pitches, which occur during acceleration and braking, seem to be a thing of the past. The unique system reacted to unevenness and turns up to 100 times per second. It's noteworthy that in such a scheme, the central processor controls each of the 4 linear electric motors individually. What does this give? For example, control of the front and rear suspension stiffness individually? If the car enters a turn, the linear motors are powered in such a way that the car mainly relies on the outer rear wheel. And such a trick gets an ultralight, unusual maneuverability. In case of a turn, the support smoothly shifts to the outer front wheel. As a result, the vehicle goes smoothly on any turns. It does not skid, it does not roll. And all this, in theory, could have been implemented in mass car production back in the 90s. But to this day, the majority of car enthusiasts drive old-fashioned, like in a brick, powered by horsepower, with dips, cranes, and tilts during a turn maneuver. The process of working on the suspension was secretive and had a misleading name. But the best suspension on the planet never went into production. Why? They say that the design proposed by the engineer had many shortcomings in the eyes of the car giant's management. The main one is the complexity and high cost of suspension production. Bouza. But on July 12, 1934, Amar Bouza died of a heart attack, and by 1970, all the company's developments were sold. If we move closer to our time, something similar was introduced in Audi. If you dissect an Audi A8, you can see the electromechanical part of the chassis in the front, which includes engines, a titanium torsion body, and struts connected to the steering knuckles. This sedan uses a platform in its work. Instead of traditional stabilizers, electromechanical drives are used for each wheel separately. The 48-volt crane control system, which used to be adaptive, has evolved into an active one. The front camera, which monitors the road conditions and captures the situation 18 times per second, acts as an all-seeing eye. The car's electronics, based on data received from the camera every few milliseconds, determine when and how to react so that no one in the cabin feels discomfort or a turn. That is, the onboard computer sends a command to the electromotor stabilizers to press this or that spring over the bump or pit. The necessary command is also received by the shock absorbers and air springs that absorb shocks. Despite many advantages, such a transport control system has a downside, which lies in the fact that the accuracy of measurements depends on the level of visibility on the road. The accuracy drops significantly in foggy conditions, for instance. Well, how do similar technologies perform in a snowy fairy tale of separate countries? Let knowledgeable people tell in the comments. Nevertheless, the developers tried their best to make the ride as safe as possible, and instilled a cleverness in the car's brain that is only used in the Audi A8 to this day and nowhere else. The car receives information about the threat of collision through the autopilot sensors, which scan everything around them at 360 degrees. If a side collision is inevitable, the active suspension magnetically lifts the dangerous side of the body to the necessary degree upwards, reducing the degree of damage from the impact. After all, in such a case, most of the load is taken by the massive threshold and the solid floor, not the doors. On that note, we will likely end our episode. Write about which engineering solutions amazed you the most, and which ones caused more skepticism than admiration. We would be happy if you rate this episode fairly and pass it on to your acquaintance, the auto mechanic, who with his professional comment will set us straight. Thank you for watching, and see you in future episodes on our channel.